Okay, so I wanted to review the very last thing that we covered before our semester was disrupted, and that is the area of planar regions. So this whole video is going to be a review of what we did in class. There's nothing new here, but just to remind us of what the very last thing we covered was so that we can move forward. So we talked about the area of planar regions, and we had said that that area is interpreted in the good old-fashioned sense. And what do I mean by that? I mean that it is positive. So it is not signed area. It is not negative if it's under the axis. It is area in the good old-fashioned sense, positive area. And we talked about one specific case. There are going to be more that we'll work our way through, but the case that we had covered was this. Region bounded above by f of x, so here's our function f of x. A region bounded below by g of x, to the left by x equals a, and to the right by x equals b. So that is the region that is highlighted here in gray. We had proceeded by setting up a Riemann sum. A Riemann sum, therefore, is based on rectangles. So if we draw just a general rectangle that you can see here in orange, then the base of the rectangle is going to be the delta x b minus a over n, but we will not actually need that information once we start using the formula. The height of the rectangle is going to be f of x minus g of x, the top value minus the bottom value. And so our general formula for a region of this kind is given here. Right? So if we set up that Riemann sum like we did in class, we'll recognize the formula for a definite integral, and the area is going to be the integral from a to b of f of x minus g of x dx, which is very often given in sort of a memory aid kind of way as the integral from a to b of the top function in terms of x minus the bottom function in terms of x. So top minus bottom from a to b dx. Okay, so that was the general idea. Then we've moved on into a specific example. So we're going to go ahead and redo that same example. Again, this has been done in class, but we are going to redo it now, and then the next video will contain new problems and new information. So we're going to work on this worksheet that was handed out in class, and will also be posted for you soon online so that you can have a copy of this sheet if you don't have the paper one anymore. And the sheet is telling us to find the areas of all of the following planar regions and to sketch each area. And we had done the first in class number 1, and we'll do that together again now. So this gives us a region bounded by the curves y is equal to 2x squared and y is equal to root 32x. And we noticed in class that there is no information here about which one is the top, which one is the bottom, and what these values of a and b are equal to that we're supposed to use in our formula. So we're going to start, and we did in class as well, by sketching the region, and hopefully all of this information is going to become clear to us once we have a good idea of what the region looks like. So let's draw ourselves a couple of axes here. So there's my x, there's my y. Y is equal to 2x squared, that is an upwards facing parabola. So there's the curve y is equal to 2x squared. Y is equal to root 32x, so that is a scaled root function, and so as a general root function we'll draw it like this without worrying too much about the scale. We just want to get a general sense of the region. And so we'll have here 2 points of intersection, and now that we can see clearly the region that we're talking about here, we have an answer to the first of our question. The top function is the root function, and the bottom function is the square root function. We are still missing the the x to the right and left and right values. And we can see off the graph right away that the left value, x equals a, is 0. But the value on the right-hand side, the b value, that is not obvious. So the way we found that was an intersection. We set these two curves equal, so we're looking to find the points of intersection of these two curves. And so we're going to use the comparison method, which means that we can set the two values equal to each other, or the two functions equal to each other. So 2x squared is going to be equal to the root of 32x at the points of intersection. To solve an equation like this, we're going to square both sides. So we're going to get 4x to the fourth is 32x. And there was a suggestion in class that we should just divide by x to simplify the equation, and that is something that we do not want to do. We do not want to divide by x. Why? Because we do not know what if x is 0. Right? We cannot divide by a quantity unless we know that it is non-zero. So the better thing to do is to bring everything over to one side. We'll bring over the 32x and keep our leading coefficient positive. And to solve an equation like this, we are going to factor out the common factor. So we'll factor out a 4x. That is going to leave me with x cubed minus 8, which is equal to 0. So either 4x is equal to 0, in which case x is equal to 0. So that is our first point here with the a value. Or x cubed is equal to 8, which is going to give me x is equal to 2, which is the b value that we were looking for. So we now know the top function, we know the bottom function, we know the a and the b, and so we can use our formula. So the area that we are looking for, let's rewrite the formula again, the area from a to b. I'll write it in its sort of memory aid fashion. The top of x minus the bottom of x dx. And now that we know all of these pieces, we can just fill them all in. So we had just said our a value is 0, our b value is 2. The top function was the root function, so root 32x minus the bottom function is 2x squared dx. Now that we have that set up, we can just proceed and evaluate this. So the first thing that I'm going to do is split that root. So I can write this as root 32. The root of x I can write as x to the 1/2. 2x squared I'll leave as it is. And now we can just anti-differentiate. So we're looking for an antiderivative that we are going to run from 0 to 2. The antiderivative, well, we can keep the coefficient root 32 in front. The antiderivative that we're looking for here, x to the add 1, so 3 over 2, divided by 3 over 2, which is the same thing as multiplying by 2/3, minus x cubed over 3, which is the same thing as multiplying by 1/3, so there is our antiderivative. We're going to run this from 0 to 2, so if we do that, we're going to get root 32. Well, 32 is 2 to the 5th, so I'm going to write that as 2 to the 5th to the 1/2 times 2/3, and then plug in the top value, x, which is 2 to the 3 over 2, minus 2/3 of 2 cubed, well, so there you go. You see that I've got an email. Whoops, I thought I'd turned off my notifications. I will make sure to do that on the next video. We here are going to then subtract, plugging in 0, and so I'm going to get, well, 0. I'm not going to rewrite the coefficients because everything is going to give me 0 here. And then the last thing I need to do is simplify. So let's pull out the 2/3. We'll get 2/3 pulled out here. 2 to the 5th to the 1/2 is going to give me 2 to the 5 over 2. Times here 2 to the 3 over 2 remains. I've pulled out the 2/3, so this is minus 2 cubed which is 8. So let's simplify that a little bit more as well. 2/3 times, I'm going to add the two exponents, right? So that is going to give me 8 over 2. This is to the 8 over 2, which is 2 to the 4. Minus 8, 2 to the 4 is 16. So 2/3 times 16 minus 8. 16 minus 8 is 8. 8 times 2 is 16. So 16 over 3. This is area, so I should probably write units squared. Okay, so that's the end of the review. That was done in class. The next video will go on to the next problem that we see down here, problem number 2.